Yeah, now everything is fine, right?
Yeah, it's good.
Yeah,
good.
okay, good.
Okay.
Yeah, thank you. Yeah, thank you, Pratik, for the invitation and for for introducing me right now. As Pratik said, I'll be talking about basically about algebraic natural proofs and our recent works around them, two of them. So basically, this is going to be what we have observed about natural proofs, or I have observed about natural proofs in the joint works with Prerna Chatterjee, Mrinal Kumar, C. Ramya, and Ramprasad Saptarshi. And Mrinal is at IIT Bombay, rest of us are from TIFR. Okay, so this is the plan. So I plan for this talk to not go longer than 45 minutes, but maybe we'll spill over if there are, if people are interested in the details of the proof and so on. So within the first 15 minutes or so, we'll just go over some algebraic complexity basics for in case there is someone who is not very familiar with the literature and some of the subtleties. Okay. Then in the next around 20 minutes or so, we'll look at algebraic natural proofs. We'll define what the algebraic natural proofs framework is and so on, and try to make sense of all the things that are known about algebraic natural proofs, or some of the things that are known about algebraic natural proofs. And then after that, if there is some time, then we'll just go over the proof idea. Okay. And as Pratik said, in between, if you have any questions, unmute yourself and ask the question, or just put it in the chat. Okay, so let's get started. Okay, so what is algebraic circuit complexity, right? So we deal with multivariate polynomials, okay, and the models that we work with are called algebraic circuits. Okay, and they look something like this. So you'll have a directed acyclic graph, okay, so as the one shown here, right? And so how will it look like? So there will be some leaves, which are basically nodes that don't have incoming edges into them. They'll be labeled with either variables or some constants from the field. Okay, so when I say field, just think of complex numbers unless I mention otherwise. Okay, and then this DAG will compute a polynomial in a very natural way. So the addition gates will compute the sum of the things that are going into them. Okay, and multiplication gates will multiply. Okay, and the parameter that we'll be interested in, at least for today, is just the size of the circuit, which is just the number of gates, how many gates are there. And it is, it should be noted that this, if the size of the circuit is also kind of the number of operations that it has to do, the minimum number of operations that it has to do on any input. Okay, so for the purpose of this talk, we'll just be working with polynomials that are low degree. Okay, so the degree d will be polynomial related to the number of variables n, and we'll usually be using n and d for number of variables and degree and so on, right? And okay, so we'll also define what is called the size of a polynomial. So because we have a nice model, we have a nice computational model of algebraic circuits, the size of a polynomial will be the size of the smallest circuit that computes the polynomial f. And this almost exactly coincides with the minimum number of operations, addition, multiplications, you have to do to evaluate f at any point. Okay, so this is a nice complexity theoretic notion. Okay, so now that we have a computational model and we have a class of interest, which is the class of all multivariate polynomials, we have to define what are easy polynomials, or what we can call efficiently computable polynomials. So this was like first formally defined as a problem first formally studied in Valiant's paper in 1979. So after him, this class is referred to as Valiant's P, or VP for short, right? So it's like the P class for algebraic circuits, right? Yeah, so VP basically has n-variate polynomials f, whose size is polynomially related in the number of variables n and the degree t. But since we are looking at d being poly n, this basically means that the size is also a poly n, right? And an example is the determinant polynomial, which is it's called a symbolic determinant polynomial. So you basically take an n cross n matrix, and every entry is a fresh variable xij. Every entry the ijth entry is a fresh variable xij, and you take the determinant of this n cross n matrix. So this will be the nth polynomial, the nth determinant. Okay, and this polynomial has efficient circuits. Has small circuits. So this is an example, and it's a very canonical example of an efficiently computable polynomials. Okay. Uh, yeah. So since this is the definition for easy polynomials, the question now is what polynomials are hard? Okay, and are there even hard polynomials? And of course, there are hard polynomials because the way we have defined things. And it turns out that almost all polynomials are hard. And what this means is that if you pick up a polynomial, an n-variate degree d polynomial, so just fix d to be some polynomial in n. Okay, so just pick, and then you pick some n-variate polynomial of degree d. And if you, if you select every coefficient uniformly at random, then you will end up with a polynomial that is hard, that does not have circuits of size poly n, right? Good. So, but that does not mean that everything is done. Then the question that someone might ask you is, can you tell them a hard polynomial? Can you tell them explicitly what polynomial is hard? And yeah, so that turns out to be like not an easy question to like solve. So first of all, how do we even formalize what it means for some polynomial to be explicit? Okay, so let's try to come up with a definition and let's see what happens. Okay, so here is like one set of polynomials that definitely has to be called an explicit polynomial, right? So I want to say a polynomial is explicit if I can efficiently describe it to you, right? So what does that mean? It means that so suppose you ask me what the polynomial is, I'll tell you, okay, so there are n variables and it has degree d, okay, and then you will give me some monomial of this sort. You'll tell me some monomial, and then I should be able to compute the coefficient of that monomial in my polynomial efficiently, right? Even though I cannot give you a small circuit that computes that polynomial or that implements that polynomial, I should be able to tell you the coefficients at least. And here efficiently means in time poly n and d, right? So these polynomials, at least I think we can agree that these should be called explicit polynomials. And yeah, and then yeah, so of course Valiant also like worked with these things. I mean, he also wanted to define what polynomials are efficiently describable or definable, and he came up with this notion, the notion that we now call VNP or Valiant's NP, which is basically the class of all efficiently definable polynomials. And the intuitively explicit polynomials that we just spoke about are all efficiently definable polynomials. They are all in VNP. And in fact, yeah, so yeah, and so okay, so what is, so I won't define VNP explicitly. I mean, I won't define VNP explicitly right now. So, but a good example to keep in mind is the permanent polynomial. So permanent is a slight variant of the determinant. So it looks like the following. So suppose you want the nth permanent polynomial, then you will go over all permutations on n objects, right? And then for every permutation, you will create the monomial for that permutation, which is just xi comma sigma I. Okay. And as you can see, if you put signs here, I mean, if you put +1 or the sign of the permutation here, you get determinant. So basically permanent is like a very close cousin of determinant. Okay. And it also happens to be complete for the class VNP, for whatever that means. So basically, I mean, why did I tell you that information is because then whenever you want to think of VNP, just think of permanent. And yeah, and most of the things should be, you should be able to deal with VNP well, reasonably well. Okay. So yeah, so with all this background, so what did we want to do, right? We wanted to find an explicit polynomial outside VP. Okay. Which, what does that mean? We mean that we wanted to find an explicit polynomial that was not easy, right? Or which was hard. We wanted explicit hard polynomials. Okay. And because of this, the definition of VNP being so close to the the intuitive notion of explicit polynomials, what this means is that this question is essentially equivalent to the VP versus VNP question, which basically means is VNP contained in VP? Because VP is trivially contained in VNP. Anything that is efficiently computable is also efficiently describable. Okay, and because of the canonical examples we had seen, it's also the question of determinant and determinant versus permanent. Okay, so it sort of means that is so does permanent and the determinant have roughly the same complexity? That's the question. Okay, so just to put things in context here, right? So permanent, if you don't know, is complete for sharp P, I mean, if you look at it as a Boolean like thing, and it's a Boolean search function, a Boolean function as such. Okay, which is, I mean, the problem is the counting version of the SAT. I mean, the 3 SAT or anything. Yeah, so this is really hard, and determinant we know is in NC. I mean, it has polylog. I mean, it has poly-size circuits of polylog depth. So it is like efficiently parallelizable polynomial. And on the other hand, sorry, not a polynomial, a function. And on the other hand, we have something that is like Sharpie complete, right? So this is a massive separation. This is a huge separation, and yeah, so we believe that this is an easier question than the P versus NP problem, right? And also, I mean, if some really minor things work out, then if P is not equal to NP, then VP is also not equal to VNP, and so on. Yeah, but yeah, so the crux of the matter is that VP versus VNP is a much simpler question. I mean, is at least believed to be a simpler question than P versus NP. So we would expect this to be solved before P versus NP is resolved. Okay, so yeah, so at this point, are there any questions with all this background? Okay, I guess not. Okay, so then cool. So then what? Okay, so then what did you want to do again? So right, so our goal was to find an explicit polynomial that is outside VP. Right, we want to prove super polynomial lower bounds against algebraic circuits. So where have we reached? So currently, the best circuit lower bound that we have, it looks like omega of n log n. Right, it's not very good. I mean, it's not very massive. Yeah, and this is, I mean, to make it even worse, this lower bound goes all the way back to roughly 40 years before today, right? And we have not seen a better circuit lower bound since then. Okay, but that said, I mean, so of course, then what happens in complexity theory? Usually, people have considered simpler questions by putting more structure on models. I mean, the models that we consider circuits and so on, right? And then what we have is the following, like a massive body of research which has really good lower bounds, so exponential in n to the epsilon, right? So exponential root n kind of lower bounds against homogeneous constant depth models, and quasi-polynomial lower bounds against multilinear formulas, and exponential lower bounds against some non-commutative models, and even monotone circuits. So it's okay if you don't understand all these terms. What the main message here is that in structured models we have made reasonable progress, right? So then the question is, why has this progress not translated into giving better circuit lower bounds, even quadratic or some such thing? I mean, why do we not have strong circuit lower bounds? And if you think hard about it, then what you reach, I mean, the question that you will reach is the question that I've written here. I mean, you want to say that okay, there is some similarity to all the techniques that are used until now, right? And we want to understand if similar techniques can give lower bounds against VP. Can we ever prove a lower bound against VP using similar techniques, right? So that is the question that led people to algebraic natural proofs, and that is the question we'll be looking at more deeply now. So before that, if there are any questions, then
what is this epsilon here in homogeneous constant?
Yeah. So here, right? You mean here?
Yes.
Yeah. So basically, yeah. So I just wanted to combine all these results. So one of them is exponential in n, the other ones are exponential in root n, and so on. I just wanted to put something there which makes sense. I mean, does justice to all those papers.
Okay.
Yeah. But so the thing is, the main message I want to give is that we know super polynomial lower bounds in any structured settings, and we don't know even like truly super linear lower bounds are not known even against like in circuits. So that's the main message. Yeah. Okay. So let's look at what these similar techniques mean. Okay. So what we want to do again, right? We want to find explicit polynomials outside some class C. Okay. And yeah. So let's try to think of what kind of techniques might help us, right? Sorry. Right. So think of this. I mean, look at this thing here. So there is some universe. Okay. There are all sorts of objects here. Okay. And then there is this class of easy objects, which is a very small class, right? And then we also have some intuitive notion of what is explicit. So this explicit class it contains everything that is easy, but it also contains some other things which we believe should be hard, or we believe that there are things here. Okay, and usually whenever and then what we want to do is we want to find something that is in D that is not in C, and it is hard when what happens is the following: is that proving non-membership in C is hard, or hard is in, or at least we don't know how to prove non-membership in C. Right. So for instance, if C is VP, and if you give me a polynomial, I don't know how to prove that it does not have a small circuit. It somehow, and it does not make sense for me to just create every circuit and say, oh, this does not compute the polynomial and so on. Right. So there is no easy way of proving non-membership in C. Okay. So usually when such a thing happens, what we do is that we try to come up with another class or another set. Okay, this green set. Okay, and what property does this green set have? The property that we want from this green set is that, let's give some names, right? Let's call this P. The property that we want from this green class P is that membership and non-membership, both these things, or actually just non-membership is fine, should be easy. And proving non-membership in P should be easy in some way. Okay. And the other property that we also want is that it should contain C completely, just as we have drawn here. And then, then we'll also hope that the examples that we know from D, there is something that falls also outside P, right? And that would be the explicit thing that is hard. Okay, so yeah, this is the intuitive thing. Let's try to instantiate this so that things become clearer. Okay, so consider the following scenario. Okay. So suppose, let me add information in the same figure. So suppose this universe that we have is basically R to the 4, and by that what I mean is we are considering, so for now we are just considering univariate polynomials of degree at most 3, okay, and over the real numbers. The coefficients are real numbers, okay. So then every such polynomial can be described as a tuple ABCD, okay, which is in R to the 4, right? So the universe is R to the 4, all the degree at most 3 univariate polynomials. Okay, and let's say the easy class that we want to study is the class of polynomials where, the cubic polynomial that you can write as a cube of a single linear form, right? Polynomial that you can write as alpha x plus beta to the whole cube for some alpha and beta in real numbers. So that is this class C. Okay, and let's say we want to find a polynomial with moderate sized coefficients. Either integers that are of small bit complexity in some sense, or rational numbers that don't have massive denominators and so on. Right. So we want to find a polynomial with simple coefficients that is outside C. That cannot be described as a polynomial. That cannot be described as a cube of a linear form. Okay. So here is one way of doing it. So what we can do is we can just look at, so we can observe what happens to alpha x plus beta the whole cube, right? So what we are now doing is we are looking at the structure of C, right? And if we expand it, we see that alpha x plus beta the whole cube looks like alpha cubed plus, this thing, 3 alpha squared beta x squared and so on, right? So this is the A, B, C, and D for everything in C, right? And yeah, if we look at it hard enough, we might, we'll be able to see that they all satisfy this particular equation, right? So A is going to be alpha cubed, D is going to be beta cubed. So A times D is always going to be 1/9 of B times C, right? So this equation says exactly that. So what we have done is we have looked at the coefficient vectors of C and we have come up with a structure that they have. In fact, we have come up with a very simple polynomial P, or a very simple polynomial, which is this polynomial that I've underlined, okay, such that the zero set of that polynomial completely, completely consumes the class C that we wanted to study, okay, and yeah, so one thing to note here is that it is not necessary that everything that satisfies this equation is in our class C, which is not, which is exactly the case here. Not every ABCD vector that satisfies this equation is inside C, but that is fine. just like it is fine that there are things that are outside C that are in P, right? Okay, so now why is this important? So once we have this, now it is very easy to come up with a polynomial that is outside C. I just have to come up with something that is outside P and also has small coefficients. And because this equation is so simple, I can just say that this polynomial is outside C, right? Because it gives me 8 instead of 0. Right? So this is a very simple polynomial that is outside C. Okay, so are there any questions here? Doubts about this explanation? Okay, good. Yeah, so now if people have understood this, then let's take this to the next level, right? And let's try to do the same thing with multivariate polynomials, right? So this is what we had done. This is exactly the previous diagram, right? So now let's try to, so now let's try to extend the same method to multivariate polynomials. Good. So suppose we are working with invariate, sorry, what happened? Yeah, so suppose we are looking at invariate degree D polynomials, okay? Then, so just like the universe was R to the 4 here, but because every coefficient vector had length 4, so okay, we are back in complex numbers, okay? The field is complex numbers again, okay? So here, these polynomials that are invariate and degree D can be described by their coefficient vector, which is just the coefficients for every monomial in n variables of degree D, and are these many of them, n plus D, choose D many of them, right? So any such polynomial is a vector in C to the n. Right, so here now the universe will be C to the n, C to the capital N. Okay, this capital N is massive. It's like exponential in n. Okay, for D that is reasonably large in terms of n. Okay, and C and D and now some interesting subsets of C to the capital N. Right? And just as before, C is contained in D. We want to find something that is in D but not in C. Okay, so this is exactly the picture, this thing. Okay, so here is the natural, a natural recipe of lower bounds, and this is what we meant by similar techniques when we were talking about previous things. So most lower bounds kind of look this way. So firstly, we say that okay, I need to find I want to prove a lower bound against C. I want to find some weakness of this class C. Okay. And what will this weakness be? Again, it will be some equation. Okay, and this equation is now some invariate polynomial. Okay, that is not 0 by default. Of course, it's a non-trivial equation, such that if you put anything in C here, so suppose f is in C. Okay, then when you put the coefficients of f in this equation, you get 0 for everything in C. Okay, this we will call a weakness. Okay, so it's a weakness that it vanishes on this equation. It's a weakness of C that every member of C is a root of this equation. Okay, and then what the next step of this whole procedure is to find an explicit polynomial H that is in D that is not weak. Which basically it means that it does not satisfy this equation P. Okay, and so what is the guarantee that such an explicit thing will exist? There is no guarantee, but we hope to so we hope to find that we hope that such explicit non-weak polynomials exist, because so we just so we want to argue that such things exist. Argue this using the fact that Pn is simple in some sense. Right, so just as in the previous case, we had sort of a multilinear kind of an equation, this 9AD minus BC, right? And because it was simple, we said that okay, there should be some root of this, which is a very simple thing, and it turned out to be true, right? So here again, you would want to say that because this is a simple equation, right? So basically, you want to come up with a simple weakness first. Okay, you want to come up with a simple polynomial P that is a weakness for C, and then you want to argue using the simplicity of P that there should be an explicit non-root of this equation. Okay, and if both these things work, then yeah, then great, then you have your lower bound. Okay, this is what is called a natural technique for proving lower bounds, and yeah, this natural is still in quotes because I have not defined what simple is. Okay, which we will soon do. But yeah, this is the general template. So, and this should be, I mean, yeah, for the rest of the talk, this has to be clear. So, yeah, if there are any sort of questions, then please ask right now. Okay, good. Either I'm doing really well or I'm not doing well at all. Okay. Yeah, so let's move on to these equations. Let's try to understand these equations and things better. Yeah, so let's first define an equation for multivariate polynomials, right? I mean, we know what it is. We just have to write it down formally in terms of mathematical symbols and so on. Right. So again, we are looking at n-variate degree d polynomials. So the number of coefficients is capital N. Okay. So now, so let C be some subclass of C to the n, right? Which is basically, so now I'm looking at C as the set of coefficient vectors that are in it, right? And let Pn be some non-zero polynomial that is capital N variate. Okay. So we'll call P sub capital N an equation for C if, as we had said here, for every polynomial f in C, Pn vanishes from the coefficient vector of f. Right. So this is what is called an equation for C. Okay, and here, so notice here that we are not talking about the complexity of computing Pn or any such thing. We are just saying that there is some equation. Okay, good. So if this is clear, so now let's define natural proof. I mean, let's see what a natural proof is. Okay, so I mean, there are things that I have to fill here. So this notion of algebraic natural proofs is a sort of an algebraic analog of the natural proofs framework from Boolean complexity and so on. But you don't need to know that to know this. I mean, we have introduced all the required things. And this was first defined in jointly, I mean, independently defined by Grochow, Kumar. Oh, I think this is GKSS. Sorry for that. Yeah, Grochow, Kumar, Sachs, and Saraf, and also by Forbes, Shpilka, and Volk. Right. Yeah, and here is what they said. So again, let C be some subset of invariant degree d polynomial. So it is a member of C to the capital N, and let P sub capital N be some non-zero capital N variate polynomial. Now Pn will be called a natural proof for C if firstly Pn has to be an equation for C. Okay. Secondly, we want to say that Pn is just, I mean, Pn is not just some, I mean, it's not any equation, it is also simple in some sense. So I want to say Pn is in some class. So for now, let's just say simple is Vp, right? So it's in Vp with respect to the parameter n. So it has degree poly in capital N and circuit size also poly in capital N. Okay. And even further, so there is something that comes for free in the algebraic world, but let's mention it anyway. Okay, we also want that Pn of coefficient vector of H is not equal to 0 for most, in fact, almost all H that are, I mean, okay. So, yeah, it's sort of messed up, but yeah. H that are, so if you just pick a random point from this space C to the capital N, then Pn is not 0 there. And this comes sort of for free from the line above it, because Pn is a low degree polynomial, so, and complex numbers is like an infinite grid, right? So yeah, so you pick anything up from that, it will, Pn is almost definitely non-zero, right? And because, so because of this upper bound here, this is called a VP natural proof for C, okay? And in general, you can replace this VP by anything you want. It just, I mean, as long as you replace it in all three places, it's fine. So you can talk about a C prime or a D natural proof for C by replacing this with D and this with D. So whatever upper bound you put on P, will be, I mean, that upper bound will go here. We get a D natural proof. So yeah, okay. So this is the definition. Yeah. Now, are there any questions now?
Anamay?
Yeah.
So for purpose of separate for finding polynomial outside class C, so we could have defined like the opposite way also, that Pn on coefficient f bar is non-zero, but for other outside, all outside it is zero.
Yeah, but so yeah, that is sort of true. But then what happens is, so yeah, I mean intuitively, I think this thing makes more sense, right? Because what happens is, whenever you have a low degree polynomial, most of the things will be non-roots of that thing, and
Yeah, this
most things are hard. Yeah.
Yeah, third condition won't come for.
Yeah. You want most things to be like hard according to your weakness. I mean, most things to be not weak.
Yes.
Yeah. So yeah, but I mean, I can imagine a proof that would go that way. But yeah, yeah. This seems more intuitive. Yeah. Yeah. Thank you for that question. Okay. So is this clear? Cool. Okay. So then what? Okay. So now that we have defined algebraic natural proofs, right? So here is like the big dream. Okay. So when you look at this definition, this is what you dream of. You dream of a non-zero polynomial P. Okay, a capital N variate non-zero polynomial. I mean, for most, I mean, for all large little n little d, you dream that there is a non-zero polynomial P sub capital N. Okay, in VP of capital N, of course, as before, and such that Pn is an equation for VP. It vanishes everywhere on VP, and Pn is not an equation for some polynomial in VNP. Okay, or I mean, it is not an equation for VNP, which basically means, I mean, if you go back to this definition, it basically means that there is some polynomial f in VNP such that this thing does not happen. Right? This is a negation of this statement. So this is the big dream. I mean, why is this the dream? Because once you find such a non-zero polynomial P, or the family of such non-zero polynomials P sub n, then you basically have a proof that separates VP and VNP. Okay, so this is what you want. I mean, this would be great if this is true. Yeah, so I think there is a question.
I was just asking, so what is VPND?
Yeah, okay. Good question. So, yeah, so here is how it will, it will go. So this is a problem because VP is like a union over two sorts of things. So usually the way I think of this is that there is some function that grows polynomially in n. There is some function d of n. Okay, and then what you do is you look at VP, the subclass of VP, which has n. I mean, okay, you look at the subclass of VP where the nth polynomial has degree at most d of n. Okay, and then VP ND is basically the nth slice of this family of, I mean, this class of families. Does that make sense?
Yes, that makes sense.
Okay.
Thank you.
Yeah, so the thing is, I mean, I have to write this VP ND this way because unless I fix both N and D, this capital N does not make sense. But yeah, but I understand why this like bothers some people. Yeah, because it seems like if you have fixed both the parameters, then like how do you even talk about what is polynomially growing and what is not? Yeah, but this is what I mean by that. Okay, yeah, good. Thank you for that question again. Yeah, okay, so this is what we want, right? We want a family of equations for, I mean, such that it works for all large n, all large nth slices of the dth slice of VP, right? And you also want it to not work for something in VNP so that you have a separation, right? So this is what we want. And the question is, therefore, is there such an equation? Okay. Or even, I mean, so even weaker question is there any sort of family of equations, I mean, family P of equations, so that even the first condition is satisfied? No? Are there any equation, I mean, is there any family of equations for VP itself? Just let it vanish on VP, let it not vanish on VNP, right? So does VP have VP natural proofs? Yeah, that is the algebraic natural proofs question. I mean, that is the main one that people are interested in. Okay, so let's move ahead. So, or move ahead and see what we know about this question. Okay, does VP have VP natural proofs or not? So, what all is known about this? So the first work so this is the same work that I had mentioned earlier, the work that defined algebraic natural proofs. So this is the work of Forbes, Shpilka and Volk, right? So yeah, so what they showed, I mean, using some previous results, they showed that equations for simple classes are not too simple, right? So what is simple here? So this first simple is something like constant depth multilinear circuits, okay, depth 3 multilinear circuits to be precise, right? And they showed that if you are looking at depth 3 multilinear circuits, then their equations cannot be too simple. I mean, they cannot be, I mean, you cannot have a sparse polynomial that is an equation for depth 3 multilinear circuits, or I mean, any equation for depth 3 multilinear circuits cannot have small Waring rank, right? It cannot have a small depth 3 diagonal circuit, and so on. So, I mean, they showed this for a few other like super simple models and few other simple models. Yeah, but largely this was the message, that equations for simple classes are not too simple. So now how do we compare this with the statement that we wanted to know about? So how do we compare this with the statement of if there are equations for VP that are in VP, right? Okay, so the thing is, the statement is kind of like sort of incomparable, because you have, so what this statement does is it weakens both these things, right? We have gone into subclasses of both these things, so it's neither stronger nor a weaker statement, right? But at least it tells us that, I mean, it sort of gives a weak evidence, right? So this is, you can say, sort of, it's a weak evidence against the existence of VP natural proofs for VP, right? We can at least say this, because it sort of says that, look, I mean, here are some simple classes, and I mean, yeah, here are some simple classes, and for that we can already prove that such things happen. And one more thing that this was, one more reason. Because,
I had a small question.
Yeah.
So the Forbes Shpilka Volk result, is it unconditional?
Yeah, I mean, yeah, this thing is unconditional. Yes.
Okay.
Yeah. So yeah, that's what I was getting to. So they prove this result by using hitting sets for these models, right? Yeah, and how that happens, I mean, yeah, I don't want to go into the technical details of it unless we go into the proof idea section of this talk, right? So what they did was they looked at these super simple classes, and these super simple classes are things for which we have, almost like quasi-efficient kind of hitting sets, and they showed that these hitting sets can be used to prove that there are no simple, there is no simple class for which these things can be, any equation.
So, Anamay?
Yeah.
So, for whichever class we are trying to get this equation, so this equation should be in the at least in the super class of that class, right? Like, for example, here you said simple is like depth 3 multilinear.
Yeah. That's not necessary, actually. So the thing is, yeah, I mean, I understand where the intuition is coming from. So the problem is this parameter n, right? So for instance, okay, I can give you an example. Suppose you look at sparse polynomials, okay, over capital N variables, and sparse polynomials over little n variables. Then basically one equation that works for sparse polynomials over little n variables of degree d is just the monomial x1 through x capital N, and this is itself a sparse polynomial, because whenever you have a sparse polynomial, at least one of the coefficient will be 0. So this thing will be 0 over the entire over the entire class, over this class. Right?
Can you repeat? I didn't get this.
Yeah, sure. Yeah, okay. So maybe I can repeat the question for everyone else as well. Yeah. So okay, if I understand Pranav's question correctly, the question was that so suppose we fix a class C. Okay, could it happen that for some subclass of C, okay, for some subclass of C, could it happen that C has C prime equations or C prime natural proofs? Right. That is your question, right, Pranav?
Yes.
Okay. Yeah. So here, yeah. So while the intuition seems correct, the problem that happens here is that, I mean, there is a subtlety here of the arity. So the underlying arity here, while it is little n, here it is capital N. Right. So of course, little n you don't expect to be this thing, but it's not a. I mean, it cannot be a valid proof because anything that you're talking about has to be a capital Invariant thing. And one example of such a thing is if you take this calligraphic C to be sparse polynomials in little n variables. Okay, so just say little n variables and degree also little n. Okay, then because it is a sparse polynomial, of course not all coefficients. I mean, if you look at the coefficient vector of this of anything from this class, it will have a lot of zeros. Okay, somewhere. I mean, there could be some non-zero values somewhere, but most of them will be zeros. Right. So you could just so one equation for this class. Yeah, one equation for this class is x1 to x capital N.
So capital N is actually quite big by many.
Yeah, exactly. Yeah. But yeah, I mean, intuitively, I think your idea does make sense. I mean, apart from these sorts of pathological examples, I don't have a good answer to your question. But yeah, I mean, it does make sense that you might want the class to be, at least that class or maybe bigger or something.
Because in the too simple you were mentioning, I mean, for example, you stated this that 3 multilinear.
Yeah, but that so there I think it's just the I mean it might be an artifact of their proof as well, the proof technique. Yeah, but
okay, thank you.
Yeah, thank you. Yeah, okay. So yeah, so I hope this is clear now. Okay, we are sort of slightly pushed for time, but anyways, I mean, proof ideas we can anyways shrink. We can spend less time there. Yeah, but I want all these known results to be quite clear to most of the people, most of the audience. Okay, so next result that I want to talk about in context of existence of algebraic natural proofs was a previous joint work of, I mean, all of us, I mean, all Kumar, Ramya, Saptarshi, and me with Prerna Chatterjee. And in that so let's try to see what that result is. So instead of VP, okay, consider a new class, let's call it VP prime, right, in which you pick polynomials from VP that additionally also have small coefficients. And yeah, so for now, let's just say coefficients are either +1, 0 or -1. Okay, just +1, -1 coefficients, and of course 0 is also allowed, right? So VP prime is this subclass of VP where all the polynomials have really small coefficients. And strangely enough, not strangely, but yeah, I mean, so it happens to this class VP prime already happens to be quite rich. So most of the well-studied polynomials, I would say, because they come from combinatorial problems and so on, they have these coefficients, +1, -1, or 0. So determinant, elementary symmetric polynomial, iterated matrix multiplication, like most polynomials that you can think of. In fact, I mean, I would go further to say that it will be hard to find an interesting polynomial that does not have this structure. Right? I mean, if it does not work for 1 and -1, it will work for larger values, right? But usually you don't have growing coefficients in polynomials, right? So for this rich and interesting class VP prime, we showed the following, right? What did we show? We showed that for all n and d, and for all large enough n and d, and capital N defined accordingly, there is a p sub capital N which is non-zero, such that firstly, it is an equation for all of VP prime. Okay, and again here VP and D is the same as we had discussed earlier, right? Next thing is it is also non-zero, right? It is, I mean, it's not a trivial equation. It is non-zero on a lot of points h, even within this small grid. Yeah, we chose a finite grid, right? This is a finite grid of polynomials. We have chosen a finite grid. There are only 3 to the capital N polynomials here, but even within that small grid, this Pn happens to be non-zero on many inputs. Though maybe most people won't say it is non-zero on almost all inputs, but it is non-zero on many inputs, right? And additionally, of course, as we required, it is in VP. I mean, it is in VP, this polynomial P sub capital N. Okay. So this basically means that if you are right, so this essentially means that interesting polynomials in VP have, yeah, this, let's say, almost natural proofs because of this particular thing. Okay. Yeah, and one of the consequences of this is that, so note that even permanent, right? Permanent is also a polynomial that has this property. It also has coefficients that are just 1 and 0, right? So if permanent were in VP, then this polynomial, such a polynomial P sub capital N, will also vanish on the permanent, right? So suppose you, I mean, in particular, if you construct a P sub N, a P sub N, so I mean, the kind which is mentioned in this theorem, and you show that permanent or any other polynomial in VNP with +1, -1, 0 coefficients is VNP prime equivalently defined, you show that it is non-zero on the coefficient vector of that polynomial, then you will separate a VP and VNP, right? And in fact, you'll end up proving that permanent is not in VP, right? Which implies that VP is not equal to VNP. Okay. Yeah, one sort of offshoot that comes from this work also is that there is a similar statement for VNP prime using the same techniques, right? But that is not connected to this at all. I mean, the equation that you the equation that you get for our, okay, so firstly, this proof is, this argument is existential. So we show that there exist such equations. Okay, and yeah, so because it's an existential argument, one could argue that the equation that you talk about in this statement is different from the equation that you talk about in this statement, right? So this is not a cause for concern, right? And this consequence still stands despite this other theorem for VNP prime. Okay, so again, are there any questions about this work statement?
So I had a question about the Boolean thing. Like, is there some such thing known in the Boolean world? Like, is there what is the biggest class which has natural proofs? Like P definitely can't have unless all, so Razborov and Rudich. But
yeah, actually, I'm not aware of what is the largest class, but okay, but I can answer a different question that is sort of similar. So just like here, how we sort of relax the largeness criterion, as it is called, right? We said that, okay, you need not be non-zero on most of the inputs. You can be zero on many of the inputs, and I'll still let you through. So if you do that, then there is a result of Chow from 2011, I think. It is, okay, 2011, that says that in fact P by poly has these what he calls quasi-natural proofs, I think. Yeah, so I mean, he says that if you relax the largeness condition, then there are in fact even P by poly, the class of poly-size Boolean circuits, has natural proofs. Yeah, I hope that gives some information. Yeah.
Yeah, but isn't this kind of contra? So is this an evidence that VP might not have natural proofs?
Yeah, I don't know. Maybe.
Okay.
No. So yeah, maybe, okay. I'll get back to that. I mean, we can get back to that question later. I mean, I have some like opinions about why VP is not similar to P by poly. And let's get to that later. Okay, yeah, but any other question about this?
So I have a question. So suppose this VNP, the permanent actually let's say is weak on this VP equation. It could still happen that permanent is outside VP, right? Based on the diagram that you have showed. It seems to suggest that we might get that permanent on this equation vanishes, but still they are separate.
Yeah, that is true. Yeah, which is the this part. I mean, yeah, so
okay.
Yeah, correct. But I mean,
okay.
You are right. It could happen that permanent. I mean, it could happen that you come up with one equation for VP, and it also happens to be an equation for VP. Or I mean, permanent is not. Permanent is not a non-root of that equation.
Right.
But what you can do is maybe there is some other polynomial that is a non-root of that equation. Maybe some Nissan-Peterson polynomial or something.
Mm-hmm.
Or B, it could happen that there is. I mean, of course, you can always come up with another equation. And, yeah. Okay. Thank you. Yeah. So now let's look at our.
Anamay,
sure.
I had a question. So this Pn polynomial. So is there any notion of sort of minimal polynomial, something you can come up uniquely, or is it that you cannot never come up? Because you said that maybe you come up with a polynomial that vanishes. I mean, for some permanent, and then some other equation it does not. So is there a notion of that there is a unique or minimal?
I would think not. I mean, so the thing is that so maybe I'll say some things that So the thing is that if you want to capture the set VP, there are many polynomial constraints that you will put, right? So suppose you want to look at the variety that contains VP, right?
Okay.
Then you can write it. I mean, you can express that variety using the polynomials that define it. Okay, the ideal that defines it.
Right.
That ideal will have some generators.
Right.
So every member of that ideal is in fact an equation for VP.
Right.
Yeah. So it could happen that you have one of the bad generators that is
Bad
not
generators.
Yeah.
Right.
Yeah. But then I'm not sure if I'm not sure if there is some notion of minimal that comes here. Yeah, but that's a good question. I mean, I don't know an answer right now.
Okay. Thanks.
Yeah, maybe other people can answer if. Yeah. Okay. Yeah.
No, it's okay. Thanks.
Yeah. Okay. Yeah. So let's look at our result now in the last 15 minutes or something that we have. Okay. So what did we show, right? I mean, what is the title of the talk? what does that mean? We showed that if permanent requires circuits of size 2 to the n to the epsilon for some epsilon bigger than 0, which basically is long for if permanent is exponentially hard, right? Then VNP does not have VP natural proofs, right? And what do we mean by that? We mean that if permanent requires large size circuits, then no matter what family of equations you pick, P, I mean, if you pick up any polynomial P, capital Invariant, okay, or it's more like for whatever capital N you choose, I mean, for whatever family of P that you will pick, I can pick a large enough arities where I will show that this equation requires, where I'll show that of the member that you had picked, this Pn requires large size. Sorry. I mean this here. Okay. So any equation, so if permanent is exponentially hard, which we believe, which is why I've written it in a very faint font. So I mean, it's not a massive condition. It's something that we all believe in because it's like Sharpie hard and so on. So if permanent is indeed exponentially hard, then VNP does not have VP natural proofs. Right? So in particular, what this means in the context of the previous thing, because there is a similar statement for VNP prime, right? We showed, we first saw that VNP prime does indeed have efficient equations. But what this theorem in combination with this theorem means that at least for VNP, if you let go of the assumption on coefficients, then suddenly you don't have any efficient equation, right? You incur a super polynomial blow up in the complexity of the equations. Okay, so that is the statement. Okay, so now let me quickly put all these results in context, right? And then maybe we can discuss more things after that. So think of this big box as the so think of this box as all the possibilities about algebraic complexity, right? Okay, and suppose within suppose let me see here. So suppose within this big circle here, so in here, okay, within this circle, we are in the world where VP has natural proofs, right? So what this means is that we can prove. What this means is that can prove lower bounds. Yeah. This means that we can prove lower bounds naturally. Like using natural lower bound techniques, we can prove lower bounds. Okay, and within this, within this big circle, there is another smaller world where, all these small worlds where VNP also has natural proofs. Okay, note that our theorem does not unconditionally rule out that VNP has natural proofs. So it is still possible that we are within this circle. And here again, this means that we can prove lower bounds against VNP naturally, but this will also mean that we have to be careful. We have to be careful about what equation to pick to separate VP and VNP, right? There could be a natural proof of separation of VP and VNP, but we might have to be careful about it. Okay, that's what it would mean if you are inside this circle. So okay, so yeah, just to note, so when I say natural proofs without mentioning any class here, I just mean VP natural proofs, right? Okay, and now so before our work, this other circle, there's this green circle, which was just there is other green circle, which inside which the worlds that are in this green circle, permanent in all these worlds, permanent has sub-exponential size circuits, right? So this basically means that you have bigger concerns. That's what these worlds mean. About cryptography and so on. Right? Probably. You never know what will happen. If permanent has sub-exponential size circuits. Right? Okay. And what our work showed is that we just basically connected both these things. Right. This is what our work gives. Right. We showed that if VNP has natural proofs, then you are already in this world where permanent has sub-exponential size circuits. Right. And because we believe that we are outside, many more people many people believe that we are outside this green circle. What happens is, what this now means is, if you are in this circle, in this big circle, which means that if VP has natural proofs, if you believe VP has natural proofs, then any such natural proof separates VNP and VP, right? Because, that's it. Right? So any natural proof, after our work, you can say that any natural proof that is a proof, any natural proof for VP is will give you a natural separation between VP and VNP. Right? And what would be cool is if someone can, if someone can extend the scope of this green circle and take it like here. If you can make this green circle this big, then it would basically mean that if VNP is sufficiently hard, then in fact you can prove that VP and VNP are separate using a natural lower bound. A natural proof. Right? Yeah, so that's all that I wanted to say. If there are any questions, then yeah. I mean, all that I wanted to say apart from proof ideas, but I think I'm already very close to finishing an hour. So, yeah.
Can you move to the slide of this green circle thing, the result, the last result?
Oh,
The page.
as in?
You had this statement of the paper, right? This last paper.
Oh, acha. Okay. Yeah, okay. Let me go there. Go on.
Okay. VNP does not have version. Okay. And last. So the last comment which you suggested that you bring the whole box inside, that was to show that if permanent requires sub-exponential circuits.
If permanent requires exponentially large circuits, then VP also has. I mean, VP has natural proofs. I mean, if you can do that, then it will be. Oh no, sorry. Oh, wow. I was massively wrong. Sorry about that.
Then there cannot be natural proof.
Yeah. No. Okay. Sorry. What I meant was, okay, good. Thank you for that question, and I'm extremely sorry, for doing this. So okay. What I meant was, we would want to prove a result which would shrink this. Does that make sense? Okay. Let me not say something that I'm not sure about. Let me just write what I mean. So if someone can show that if permanent, let's say, requires circuits of size 2 to the n to the epsilon, then VP has VP natural proofs. So suppose if someone were to prove this green statement, then what we would have is that if permanent is hard enough, then there is a natural separation between VP and VNP, which would be great. So there is a similar result of Ryan Williams, I think, that talks about proofs against any XP or something. So or maybe proofs of separation between any class and any XP. Yeah, something. Yeah.
But the last result was that VNP does not have VP natural proof. The implication was this.
Yeah. So
now
our result is Now I'm asking for a positive thing. Yeah. So our result was that VNP does not have VP natural proofs. Yeah, this is what our result. Yeah, sorry for that thing. I think I confused some people.
Hi.
Hi, Amit.
Yeah. So this implication, right? You want based on the hardness of permanent, but like the earlier result, there you said that there is a class like this restricted class that has natural proofs, right? Like so.
Yeah.
So now combining these two, it's like separating that class from VNP. Using natural proofs, it seems that can be concluded, right? Or
sorry, can you? Okay,
so what you
sorry, go on. Yeah.
Yes.
Sorry, I couldn't hear you. Can you say that again? The last thing that you said.
Yeah. So the earlier result, like this is the latest result, but the earlier result. Can you please repeat that statement, like informally, or?
Yeah. So earlier result was. So there are two statements. First thing says that VP prime has VP equations, right? Equations that have complexity of VP, and the other result says VNP prime has VP equations. Yeah. So one way to interpret our result is that once you let go of the assumption on smallness of coefficients from VNP prime, I mean, when you go from VNP prime to VNP, the equations, you no longer have like VP equations, assuming that permanent is hard enough. Yeah. So what was your question? Sorry, I didn't understand.
Yeah, probably I'm messed up equations and natural proofs.
Yeah. So yeah, maybe okay. We can talk about this later, maybe.
Yeah. Okay.
Yeah. Sure.
Thanks.
Yeah.
I have a question about the definition again.
Okay.
So, because this is a bit subtle, I think. So you are saying some polynomial P capital N vanishes on VP, and by that you mean you fix a function D based on that depends on N, right? That is what you said.
Yeah.
And then, but then the thing is, if it vanishes on all of VP, then well, I might just I might just take an element of VP, but I can arbitrarily change its prefix. Like at any point, I can change. If I only change that sequence at a finite number of points, then I'm welcome to do so, and I will not be out of VP. Right? I can just change it at one specific point. So if your Pn, for example, is for a specific capital N, is not the zero polynomial, then I can go to that specific point and change my VP sequence at that specific point to some generic polynomial, and your P capital N would not vanish anymore.
Yes.
So this means that, I mean, that's a subtlety that basically says that you cannot have any polynomial with this vanishing behavior. So do you fix that by saying that it vanishes eventually on all of them or something like this?
Yeah. So okay, so let me write that now. Okay, so yeah, so let me just write. So okay, so let me write the definition of VP first. So what is VP, right? So let's say D is some degree parameter, right? D is some polynomial function.
Yes.
Okay. Then this thing contains polynomials. Okay, not polynomials. Let's say.
Well, it's sequences, I guess.
Yeah. So families.
Yeah, families
of polys whose nth like nth poly is firstly it has degree at most d of n, and secondly it has okay, yeah, so I want to say for all large enough. So okay, now let me make it very precise here. So yeah, so for VP it will be like there exists some n naught such that every member after, I mean, if n is bigger than n naught, then size of Fn is at most poly. I mean, whatever.
Yes.
Yeah. So what I want is that so I'll say that Pn is an equation for, let's just say VP d of n, if there exists an n naught such that for all n bigger than n naught, this Pn vanishes on the nth slice of VPDN. Yeah, so I think this will fix that, right? Yeah.
I think this fixes it. Yes. Yes, thank you.
Yeah. Okay. Yeah, thank you for that question. Yeah, these things are quite subtle, especially because VP is like sort of a union over two sorts of things. You have to first choose the degree parameter, then
Yes.
Yeah.
Hi, I have a question.
Yeah, sure.
Yeah, so this CKRST paper says that VNP prime and VP prime both have lower bounds proved in the natural methods, and you showed that inside VNP there are things harder than VNP prime, which do not have which will not have natural proofs if permanent has big enough circuits, but permanent itself is in VNP prime. So
yes, correct.
So permanent has VP equations, but
yeah. So the thing is, I mean, so yeah, when you select a so when you select a small set of polynomials, you can always I think I understand here. So the thing here is, so you need not have permanent here. You can put any polynomial that is in VNP in this place, and it will still go through. I mean, any polynomial that is exponentially, any polynomial that is in VNP, right, and is hard enough will work here. Yeah, but what you said is true. So permanent is itself in VNP prime, but the fact that we use is that
so permanent can be the candidate to observe separation between VP and VNP, but it itself will not be a PN, I guess, like will not be an equation.
So okay, so let me draw one more picture here. Okay, so this was going to be proof. Okay, but let me insert space. Okay, these things remind you, I don't care. Okay, so what has happened is the following, right? So okay, this is not to scale and everything. So this is VNP.
Yeah.
And this is VNP prime.
Yeah.
So the thing is, what happens is whatever. So if you pick up an equation P, okay. So suppose you pick up some equation P, and you look at the set of all its zeros, right? So let's say script P is set of zeros of P. Okay. Zeros of Pn. Okay. Right. Then what our result says is that it might cover all of VNP prime. So this particular thing comes from the first thing. And in fact, we say that there are some easily efficiently computable equations P sub capital N for which this happens. But what the second result says is that if permanent is hard enough, then there is no such script P which will completely include all of VNP. Right. So if you are fine with just cutting out a part of VNP, maybe you can still work with zeros of efficiently computable equations. But if you want to cover all of VNP, then no such equation will work.
Yeah, so probably what I want to say would be like the proof technique which will not be natural. The permanent will not be something, it will be non-zero on. So
no, that could actually still happen. I mean, so the point is, So what is to be looked at here is that the first result, the CKRST result, is an existential result. So it just says that there are some equations that vanish on the permanent, and all members of VNP prime. And the second result is saying that, I mean, so let's first assume that permanent is exponentially hard. I mean, so that we don't have to say it again and again. Okay. So if that happens, then the first result says that there are some equations that completely include VNP prime. I mean, whose zero set includes VNP prime. Some equations. I mean, maybe some equations don't. I mean, they don't include it at all. The second result says that no such equation can cover all of VNP. Right. So.
Okay.
Yeah.
Okay. Thanks.
Yeah. Okay.
So, can I ask if this understanding is here? So till now we can say that we can separate determinant and permanent. There might be a natural proof which separates determinant and permanent.
Yes.
But we cannot hope to separate like show hardness of all the possibly hard polynomials in whole VNP using natural proofs.
Yeah. So okay. So in that language in particular, so suppose you had some polynomial that is outside that you think is outside VNP, and it also has massive coefficients. Then there is no natural proof that will prove that that is outside all of VNP. Yeah. Yeah.
But also like so permanent is one hard polynomial in VNP, which happens to lie in VNP prime also.
Yes.
So I'm saying that so we cannot hope to separate like show hardness of other possibly hard polynomials in VNP. Like
that is correct. But if those polynomials also happen to be VNP complete, then yeah, I mean then proving proving anything in VNP prime is hard will immediately imply that they are also hard. So, yeah, but you are correct. I mean, it could happen that I mean, if you are specifically interested in, I mean, so for instance, in the weird world where everything that vanishes on VP prime also vanishes on VNP prime, and there are no equations for all of VP, then what will happen is that if you have a polynomial with massive coefficients which you want to show is outside VP, you cannot do it using natural proofs.
Anamay, I had a question. So basically, both the paper. So first paper shows that VNP prime does not has VP equations. Second paper shows, assuming the hardness, that VNP does not have VP equations, right?
Yes.
So basically, that means that in some, I mean, if you assume hardness of permanent, then VNP prime and VNP are two separate classes, right? Or,
yes. That right? Is.
Right.
Yeah, but that is. Go on.
Now permanent, of course, is in both the classes, VNP prime and VNP. But do you have any candidate or possible candidate that is in, let's say, I mean, that could actually separate VNP prime and VNP?
Oh, no. So I mean, so all that I have to do is come up with a polynomial. So let's take this sequence, no? So, sorry. Okay, I just went all the way up. Okay. Sorry. So you can look away from the screen if this is going to bother you when I scroll heavily. Okay. So you can look at this sequence, right? So suppose your sequence is, I mean, this is the family. Okay. It's basically, it looks like 2 to the 2 to the n times permanent of n. Okay. This is still in VNP, but it is not in VNP prime. Yeah.
I see. Yeah. Okay.
Yeah.
Thanks.
So Bhargav, go ahead. Yeah.
No, I just wanted to ask, is there a short reason for this restriction on coefficients in the first result?
Oh, I mean, the shortest reason is that we had a proof technique and it did not work if you allow for large coefficients, which is why we assume short coefficients. So basically what happens is you take a heating set. So I mean, you can refer to the other things or something, but okay. But in short, like the way you prove this result is that you say that we both VP and VNP have small heating sets with low bit complexity. So what you can essentially do is that you can do this diagonalization kind of argument where you take an incoming polynomial and evaluate it on the heating set, and only if it annihilates the entire heating set, you output a non-zero value. So because there is this negation that is happening, I mean, you want to map everything 0 to non-zero and everything non-zero to 0 somewhere. So you have to restrict your domain, otherwise your degrees will shoot up, which is why we take small coefficients. Yeah.
Oh, okay, thanks.
Yeah.
Yeah, so I have a general question about these algebraic natural proofs. So are there any results known, or in some context, like is this thing studied for approximative circuits, like for to separate VP and VP bar or something?
Oh, so okay, good question. I mean, I didn't mention that, but the thing is, because an equation is a polynomial, right? If it vanishes on all of VP, it will also vanish on VP bar.
Right.
Because VP bar is it's the smallest variety that contains VP. So yeah, if you vanish, I mean, you cannot be a polynomial and vanish on VP and not vanish on something in VP bar.
Right. Okay.
Yeah.
Yeah, are there any other questions?
So I had a question. So instead of assuming the hardness of permanent, is there something analogous to the Boolean setting where you assume some cryptographic, some pseudo-random generators existence, and that that shows that VNP doesn't have natural proofs?
Oh, I mean, in some sense, that is what Razborov. So the thing is, because Razborov and Rudich's result shows that if there are strong enough cryptographic generators, then P by poly does not have natural proofs. It also means that NP by poly does not have natural proofs, because anything that vanishes on all of NP by poly will also vanish on P by poly, because it's a subclass of NP by poly.
Okay. No, so I wanted, is there a algebraic analog?
Yeah, I mean, so the honest answer is that I don't know if there is an algebraic analog of pseudo-random generators that is not like something like succinct hitting set generators. Or I think this whole I mean this whole project of algebraic natural proofs is to try and understand what is the correct notion of algebraic pseudo-randomness, I think. Or one of the things that comes out of it is that I would say that, but I mean it's just an opinion. I mean I'm not sure if that is correct.
Okay, thanks.
Okay, if there are no other questions, then I will thank Anamay for wonderful talk and answering so many questions. Yeah. Okay. Thank you everyone for joining. That's all for this talk.
Thank you everyone for attending.